This is Jack Jackson. In our previous video we were considering the condition where we had side angle side given in a triangle. We found that that always determined exactly one triangle. So now we're going to look at a different condition, the side 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 condition. That is, we're given three side lengths for triangles. Number one, does it even make a triangle? Is that possible? Do they always make a triangle? Sometimes, or always, or never? And that's the first question. The second question is, if we do get a triangle, does that triangle have to be, does that have to determine the angles, or are there possibilities, more than one possibility for the angle? So we want to investigate that. In this particular one, we can investigate by the three side lengths given by these sliders up here, side lengths A, B, and C, which will be color-coded blue, red, and green, and marked with 1, 2, and 3 little marks respectively. So if we want to make our triangle, we want to first by starting by a point B, and then we want to go out a length A from that. So we make set our compass to length A, mark that, and pick any point we want on C. We could have picked B anywhere we want, but once we pick B, we have to pick C somewhere, anywhere we want, but on this circle. And so that gets length A the right length. Notice that is controlled by this slider. So once I specify that, it's fixed. Okay, and next let's take a let's show a red circle that's going to be centered at point C, and it's going to be of the same length as B. So if we were doing this with our compass and our ruler, we would measure this distance here with our compass, or take that distance and set our compass to that distance based on the ruler, and we make a circle. So we know that third vertex has to be somewhere on this red circle. Now we know we have two of the vertices already, B and C. We just have to locate A. Now, likewise, we can set our compass to the length of this length C, and that gives us a green circle. So what does that tell us? Vertex A also has to be on the green circle. Well, if you look at it, we only have two possibilities where the green and red circles cross, right here and right here. We can actually pick any one of those, either one of those, and we get these two possibilities for triangles. However, it turns out if we measure the angles on them, which you can see over here, it doesn't matter which ones we pick, and no matter how we pick these lengths, when we get these two triangles here, these triangles are actually just mirror images of each other, and so they're actually congruent triangles. So even though we do get two different triangles in the sense of mirror images, they are both the same triangle in the sense of their size, in the sense that they're congruent. So does the side 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 condition guarantee congruent triangles? And yes, the answer is yes. It results in at most one size of triangle. Now the next question is, can any three positive lengths be chosen and one triangle is formed, or are there conditions that must be placed on the lengths? And the hint is, what if we chose a long length for A and short lengths for the others? And so if we choose a fairly long length here, say for A, but we choose a short length here for these two, what are we looking for? We're looking for a place where the green circle and the red circle meet. But if they're too short, then this is not going to work. And so the problem is that these, well, what condition do we have? Okay, what condition do we have on these? Well, notice that if these are too short, we don't get a triangle. Well, if you notice, if they are just right so that they're the same length, when you add these two B and C up together and get the same length as A, then that makes a line segment here, which is still not going to be a triangle. So what has to happen is you have to be able to add lengths B and C together, and it has to be more than the length of A, the longest side. Or in general, add any two lengths and get more than the third one, and that's called the triangle inequality. The sum of the lengths of any two sides of a triangle must be strictly greater than the length of the third side. So hide a couple of things here, and I'm going to hide the directions, and I want to show the actual theorem. It says here, if any three positive side lengths are chosen, then there will either be 0 such triangles possible, and that will happen if the sum of the two shortest sides, two side lengths, is less than or equal to the length of the longest side, or you'll get one triangle possible. In other words, all such triangles are congruent if the sum of the shortest two side lengths is greater than the length of the longest side. That's one way to think of the theorem. And the other way to think of the theorem is, given any two triangles, so you actually have triangles, with all three corresponding pairs of sides congruent, the SSS condition, then the two triangles must be congruent. Now, as with the, we can show the side lengths and show the angle lengths there. But as with the other sketch with the side angle side, we can experiment by trying all kinds of different possibilities here for lengths. Okay, and we'll come back and investigate this a little bit more in our next sketch, where we can actually type in the numbers.